Hola, hi, this is Al, your probability and statistics instructor. Let's get to work. In this video, we are going to talk about the concept of expected value. But now, what we're going to be doing is extending that idea to the bivariate case for bivariate probability distributions. Let's begin. So first, let me show you the definition of expected value. The first one is for discrete probability distributions. Okay. As you can see, it is extremely similar to the univariate case back when we were dealing with random variables. Okay. But now this, right, instead of being a probability mass function, it's just a probability function that depends on y1 and y2, values of y1 and y2, right? Because we have a bivariate probability distribution. Same goes for the continuous random variable case. So if you want expected value of a function g of y1 and y2, now instead of having a single integral, you have a double integral. You have that function g that depends on y1 and y2, and instead of having the PDF, the probability density function, now you have the joint density function. But can you see that it is extremely similar? It is just an extension of the definition we had before. Okay. Let me show you something more. Remember this? When we talked about random variables and properties of expected values, we said the expected value of a constant is the constant itself. Same thing here, same idea, and the proof will be the same, basically. The only difference would be that you would be using double integrals instead of just one integral. Okay? There's one. Again, now you have a constant times a function, g, and we know that you could factor out that constant, and then the expected value of a constant times a transformation g, right, is just you factor out that constant and it's going to be c times the expected value of g. Okay, and again, the proof relies on the linearity of double integrals. Okay, so but we know that double integrals are just doing an integration twice, right, and just being careful with the lower and upper limits of those integrals. Again, proof extremely similar to the one we did together when we talked about random variables, the univariate case. Remember that theorem? The expected value of a sum of expected values. Again, it holds for the bivariate case, for the multivariate case anyway. And again, the proof would rely on the linearity of integrals. Now, it turns out that if this result is important, that if y1 and y2 are independent, and then you come up with transformations g and h of those random variables, the expected value of g times h equals the expected value of g times the expected value of h. Okay? A particular case that is going to be important for us in the future when we talk about covariances, okay, is this. If h and g happen to be just, here we're talking about functions of random variables. So if g of y1 is just y1, okay, and h of y2 is just y2, it's a particular case, right? Turns out that the expected value of x times y equals expected value of x times expected value of y. So basically, that if you have that x and y are independent, the expected value of their product is the product of expected values. Okay, and again, this is going to be important when we talk about covariances. Okay, just to give you an idea of how these proofs work. So we know that the expected value of a transformation is that transformation times now the joint. Okay, and we want a double integral. I'm showing you the proof in the case of two continuous random variables. But can you see? Transformation times joint PDF. Now instead of having an integral, we have a double integral. Now we know that if x and y are independent, the joint is the product of the marginals, so something like this. Now we're integrating with respect to x first, so y and f of y are constants with respect to x, so we end up with this integral here with respect to x. When you see this, you immediately go, oh, integral from negative infinity to infinity of x, f of x dx, oh, that's just the expected value of the random variable x. And then this guy is a constant, so by the linearity of integrals we get to factor it out. It's outside. Now we have the integral from negative infinity to infinity of y f of y with respect to y, and this is just the expected value of y. Okay, so if x and y are independent, then the expected value of x times y equals expected value of x times expected value of y. Okay, and that's it. So the independence was important here because we were able to decompose to re-express the joint probability density function as a product of the marginals. Okay? Okay. So now let's talk about an example. Let's do an example together where we find expected values, and we know that variances are expected values deep down, and in this case we have the expected value of a linear combination, okay, or the expected value of a sum, if you will. So we are going to apply some of those results just to make sure that we feel comfortable with them. Okay, so first let's talk about this guy, right, the expected value of y1. Let's do it step by step. Let me, instead of using y1 and y2, I'm going to be using x and y, okay, so I don't have to type too many subscripts. Okay, so I want f of x and y, that is going to be 6 times 1 minus y instead of y2, and we have some restrictions for y1 and y2, or I'm going to be using, as I said, x and y. There we are. Okay, and we have that this random variable, well, that this joint PDF is 0 otherwise. So what we said for part A, we want the expected value of y1, right? Oh, well, of x, because I relabeled these guys, right? Anyway, so instead of y1, x, instead of y2, y. So we have 6 times 1 minus y, and x is less than or equal to y. And we want the expected value of y1 and y2, that is the expected value of x and y. And again, I just made that change so I don't have to type that many subscripts. Okay, so here we go. We have two ways. We're going to do this one two different ways. One using the marginal, the other one using the joint. Let's use the joint. Okay. So basically, using one of these results that we just talked about, let me show you this one here. Yeah, expected value of g is just that function, that transformation g, times the joint PDF. Okay, so that's what we're going to be using here for this exercise. Let's apply. It's going to be that double integral. I'm going to be careful with those upper and lower limits in just a sec, but it's just x, because that's my g function, times the joint. The joint is this guy. Now I'm going to be integrating with respect to x. No, with respect to y first, and then with respect to x. Okay, let's do the integral with respect to y, and then we're going to do the integral with respect to x. Okay, so no, let's do it with x first and then y. It's if we're careful with the limits, we know that there's a theorem, a calc theorem, Fubini's theorem, that tells us that you could do the integral with respect to x and then with respect to y, or with respect to y and then with respect to x. Okay, so if we are careful, we end up with the same answer. Okay, anyway, let's do it with respect to x first. Note that x is restricted to be between 0 and y. Okay, just from the conditions of the joint PDF, x must be between 0 and y. So since I'm integrating with respect to x first, would be from 0 to y, and then y can, vary from 0 to 1. Another way of seeing this, you could make a graph of these inequalities to have a graphical idea of what that region looks like, of what the support of the joint PDF looks like. Okay, we've done it before in the past, doing that sort of graphs. Okay, so let's do that integral. Note that we are integrating with respect to x first, so this is a constant with respect to x. 6 times 1 minus y is just a constant. So I'm going to be factoring that out. Let me just take this. Oops. Come on. Okay. And I just want to point out that what I have here is just that integral with respect to x, right? Okay. So that's an easy integral, right? The integral with respect to x of x, that's just going to be x squared divided by 2. Agreed? So that's just x squared with respect to, well, x squared divided by 2 if we are integrating with respect to x, right? And we have to evaluate here at 2 different points, y and 0. So next step, when we evaluate at y, we end up with y squared divided by 2. When we evaluate at 0, just 0. Okay? So let me just write down what we end up with. So we have y squared divided by 2. Okay? Now let's try and simplify this. 6 divided by 2, that's just going to be 3, and then we're going to have 3 times y squared times 1 minus y. Agreed? Let's do that. So 3 times y squared come on. Okay, that's better. Okay. So, now, we would like to find that integral. Let me remind you that we have seen something like this before. When you want to integrate something from 0 to 1, that looks like y to the something times 1 minus y to the something. Okay? So that guy looks like a gamma, well, sorry, like a beta distribution. So I'm going to be using the beta distribution to find that integral. So y squared is the same as y to the power 3 minus 1. 1 minus y is the same as 1 minus y to the power, oh, come on, to the power 2 minus 1. Oh, come on. Oh, why am I getting this ugly display? Let me try again. Just this. Oh, never mind. So 1 minus y power 2 minus 1. Okay. Let me get rid of that guy. Okay. Better. Now, as I said, I would like to have a beta distribution. Okay, we know that beta distributions, you can take a look at, I think it's page 837 from your textbook, and there you will find the expression for a for a beta distribution, rather, right? So we know that the constant that you want if you are to have a legit beta distribution is gamma, the gamma function evaluated at alpha plus beta divided by gamma evaluated at alpha and gamma evaluated at beta. Agreed? Right? So, but now we are multiplying by this, we're dividing by this. Those are constants, right? So if we just multiply by this, gamma at 3, and gamma at 2 and divide by gamma at 5, we're not doing anything wrong. It's just a 1. Okay? But now what we have is that this guy here is a beta with parameters 3, a beta distribution with parameters alpha equals 3 and beta equals 2. So this is just a 1, and this is going to be 3 times gamma at 3 happens to be what? Remember that by those properties of gamma functions, this is going to be 2 factorial, right? Then what we have here is gamma of 2 is just 1 factorial, and gamma at 5 is going to be 4 factorial, right? But 2 factorial is just 2, and 1 factorial is just 1. So we have 3 times 2 times 1. So we have 3 times 2 times 1, which in turn is just 3 factorial divided by 4 factorial. But 4 factorial is the same as 4 times 3 factorial. Sorry. So in the end, what we have is 3 factorial divided by 4 times 3 factorial so expected value of x, guess what, is just 1 over 4. Okay, make sense? Of course, you can do the math, right? It could have been another way. It would be just y squared times 1 minus y would be y squared minus y cubed, and then you use the linearity of integrals and find those two integrals, the integral of y squared minus the integral of y cubed, and that's it. Okay, so just I like thinking in terms of probability density functions. Anyway, so 1/4, that's expected value of y. Let me show you another way from our lecture notes. So this is the problem that we wanted to solve initially, right? Another way is, guess what? Find the marginal of y1 first. Okay? So if you find the marginal of that guy first, then all you have to do is do what we did before. Use the expected value for a univariate, for a random variable. Okay? So that's what we have here. You find the marginal, right? And then it's a regular expected value. No need to do double integrals. Okay, but can you see that it was 1/4? Okay, you do the same for y2. You could find the marginal, and then it's a regular expected value, the kind that we had before. Okay, let me remind you where we had those marginals. Okay, it's from this example. We did this exercise together, so we found the marginals for y1 and y2. So here in this case, right, the marginal was 3 times 1 minus y1 squared, right? And then just, as I said, would be the old expected value, right? The integral from 0 to 1 of y times that PDF, that univariate probability density function. Okay, same goes for y2. You find the marginal, and then you apply the definition of expected value just for one random variable. Okay? Okay. But now you saw that if you're careful, right, you end up with the same result using double integrals as well. Okay? Make sense? Okay. Now let's try and do part B. Okay? For part B, what we want is to find the variance of x and the variance of y. Okay? So let's talk about the variance of x here in detail. So since what we said here is that one way is finding the marginal first, let me go back to our lecture notes and let me see what the marginal looks like for y1. If we took that route, okay, so f of x is going to be 3 times 1 minus x squared. Okay, so let me write that down. Okay, 3 times 1 minus x squared. So marginal of x is f of x. We said it's 3 times 1 minus x squared. 3 times 1 minus x squared and this guy lives in the 0, 1 interval, right? Agreed? And it's 0 elsewhere. So what I want you to note is this. Note that x has what kind of distribution? We could rewrite this like a 1 is just x to the 0 power. I'm sorry, yeah, x to the 0 power, which is the same as x to the 1 minus 1. X squared is 3 minus 1, right? So when you look at it that way, and you can check that this constant is the right constant, you realize that this guy has a beta distribution with parameters alpha equals 1 and beta equals 3, right? Now from our table we have, let me find that table so you know exactly what I mean. Okay, I found that table. If you go to your textbook to page 837 and then page 838, you'll find that table of famous probability distributions. So for a beta, we have that the mean is alpha divided by alpha plus beta, and the variance is alpha times beta divided by alpha plus beta squared times alpha plus beta plus 1. Okay, so from that table we have that expression: alpha times beta, alpha plus beta squared times alpha plus beta plus 1. Okay, so from our table what we have is that the variance of x equals alpha times beta divided by alpha plus beta squared times alpha plus beta plus 1. Okay, so in this case what we end up with is alpha times beta, it's 3, alpha plus beta, that's 4 squared, and then we have alpha plus beta plus 1, that would be 5, right? Okay, so what we have in the end is 3, 4 squared is 16 times 5, that's 80. That's it. And we got that because we were able to identify that the marginal was a beta distribution. Otherwise, well, you could have found it in a different way. Okay. Another way would have been, let me show you this. An alternative solution would be, well, just find the expected value of y1 squared or x squared using our labels, right? So since you have the marginal, then you find the expected value of y1 squared the old way, right? You could do it also. We have seen that you could use the joint PDF, and it's the same thing, right? And as you can see, the variance is 3 divided by 80. Okay, so different routes to do the same. For the other one, you know, you proceed in a similar fashion. You could either find the marginal first and then find the expected value of y2 squared, or you could identify the distribution. Okay, and in that case, it turns out, I think that we also have a beta distribution, right? So you could find it also using the same trick that we used for y1 or for x as we relabeled it. Okay? Okay, so finally, let's try and do the last part, part C. So we want the expected value of y1 minus 3 times y2. Okay, so using my new labels here, we want expected value of, instead of y1, I'm going to have x minus 3 times y. X minus 3 times y. Okay. So in this case, what we have to remember is those properties that in the bivariate case, we are going to have basically the same properties that we had before, right? Expected value of a sum of expected values, and then I'm going to have this expected value of a constant times a random variable. Is just going to be the constant times the expected value of my random variable. So we get to factor out that 3 in this particular case. Right? And well, the expected value of x, we already have that guy here, is 1/4. the expected value of y, we must have it here, is 1/2. Okay, but it's going to be 3 times 1/2, and that's it. Then we just do the math and we're done. So 1/4 minus 3 divided by 2. Common denominator is going to be 4. Oops. So what we have here is just 1/4. Oops. 1/4 minus 6/4. So just minus 5/4. Okay. And that's the expected value that we wanted. Okay. So let's summarize what we did here. Okay, and you can find the solution also here. Basically what we did. Let's summarize what we did here in this video. What we did is we talked about the concept of expected value in the bivariate case, when you have a bivariate distribution. Okay, you could, in this case we talked about an example where you have a joint continuous a joint probability density function, meaning you have two continuous random variables. Okay, but the ideas are similar in the case of discrete random variables, and basically what I wanted you to see is that those properties that you know and love from expected value in the univariate case are easily extended, generalized to the bivariate case. Okay, well, that's it for now. Thank you so much for watching. Please take care and keep working hard. See you next time. Bye.